Hello everyone. Today we are going to discuss about the SCR. SCR means silicon control rectifier. Okay, now let's see what a SCR. SCR is a silicon control rectifier or semiconductor and semi-control rectifier. Okay, why it is called a semi-control, that we will discuss. If you see the symbol of the SCR, so this is a symbol of the SCR which is having, there are four layers, P, N and PEN. There are four layers and the three junctions, J1, J2 and J3, and three terminals, anode, cathode and gate. This is the symbol of the SCR. So this is a simple symbol, anode, cathode and the gate, which is having the three terminals. It is looking like PN junction diode only, but it is having one extra terminal, that is gate. Okay, because of this gate only we can switch on the SCR. That's why it is called as semi-control device. The SCR is a 4-layer and 3-terminal device. 4-layer and 3-terminal device. The 4 layers made up of P and N layers. P layer, N layer, P layer, N layer. It is made up of P and layers. These 4 layers. And are arranged alternatingly. We are arranging PN and PN alternatingly such that they form the 3 junctions J1, J2, J3. J1, J2, J3 are the key junctions, and 3 terminals are namely anode, cathode and gate. These 3 terminals, anode, cathode and gate. These are the 3 terminals. The SCR made of silicon because compared to germanium, leakage current in the silicon is very small. This SCR we are made up of silicon material. If we use the germanium, the leakage current will be very low in the germanium material. That's why we use silicon. Okay, the silicon material we use. But if you use the germanium material, in germanium material the leakage current is very high. That's why we don't use germanium material. In silicon the leakage current is very low. That's why we use the silicon material. Okay, now if you see the PN junction diode is called as an uncontrolled device. Sorry, PN junction diode only. PN junction diode, that is it is a diode. That is the symbol of the diode is, this is the symbol of the diode. This is the symbol of the diode. It is called as an uncontrolled device. It is called as uncontrolled device. Why it is called uncontrolled device? Because it is defaultly, when the diode is in switch on, it is defaultly, it is starting from 0 point and ending at pi degrees. Again in the second cycle it is starting from pi and again 2 pi degrees, and like that it is starting and ending point is fixed. Starting point is 0, ending point is pi, and the starting point in the second cycle starting point is pi and the ending point is 2 pi. So like this, the starting point is, ending point is not in our control. The defaultly it will on and off will be going on like this. That's why this diode is called as an uncontrolled device. While if we take the SCR, this is the SCR symbol which is having anode, cathode and the gate. It is called as a semi-controlled device. This SCR is the semi-controlled. It is a semi-controlled. This is the SCR symbol. It is semi-controlled because if you take the voltage waveform, assume that it is a voltage waveform. It is starting from, it is starting point. Suppose if you want to switch on the waveform, the output should start from after 30 degrees. Then you have to give the gate signal after 30 degrees only. This gate signal we will give, we will assume that we will indicate this gate signal by the firing angle. The delay angle we will give by using this gate signal. So this firing angle is denoted by the alpha. For example, assume that it is 30 degrees. Alpha is equal to 30 degrees. Here, if we give alpha is equal to 30 degrees, here it is alpha. This gap is called as alpha. So this means the waveform will start from after 30 degrees. Then if you give 40 degrees, it starts from 40 degrees only. Okay, that's why this starting point, it is in our control, but ending, it is ending at default, it is pi degrees only. Okay, it is pi, it is 2 pi, and it is 3 pi. This, it is starting from this, after 30 degrees it is starting. So this is 0 and it is 30 degrees. Okay, from 30 degrees to pi degrees. And again, it start from, it will again, it will not start from the pi degrees. Pi plus alpha. Pi plus alpha, alpha means 1, pi means 180, 180 plus alpha. Alpha means 30 degrees. 180 plus 30, that is from 210 degrees it will start in the other cycle. So it is starting from 30 degrees and ending at pi degrees. Again, it will start from pi plus alpha, that is 180 plus 30, that is 210 degrees. From 210 degrees it is starting, because we are giving the gate signal, that is firing angle is equal to 30 degrees. This means this SCR should start from 30 degrees only. Okay, that's why it is called as semi-control. This starting of this waveform, this output, that is in our control. Always when the device, if you want to switch on the device at this point, okay, that is in our control. That's why it is called as semi-control. But this switching of the SCR is not in our control. Only switch on the SCR is our control, but switch off is not in our control. It is defaultly switching off at pi degrees only. But if you want to switch on at alpha is equal to 45 degrees, it will start from 45 degrees. If you give 60 degrees, 60 degrees, based on our input signal, then it will react. Okay, that's why this switch on the device at which angle, that is in our control, but switch off is not in our control. That's why it is called as a semi-control device. Okay, next we will see what are the modes of SCR we are having. Next, here also same, it is not starting from the 2 pi degrees. Here it is starting from here, it is starting from pi degrees and it is starting from 2 pi degrees. But here it is starting from alpha degrees. It is starting from 0 degrees, but it is starting from alpha degrees. Alpha degrees means 30 degrees. And again, in the diode, it is default, it is starting from pi degrees. But here it is not starting from pi degrees. It is starting from alpha plus pi degrees. Here also same, 2 pi plus alpha. From 2 pi plus alpha degrees, it is starting, not from the 2 pi here. But here it is default, it is starting from pi degrees and ending at 3 pi. But it is ending at 3 pi, but starting from 2 pi plus alpha, because alpha we have given as 30 degrees. That's why it is called as a semi-controlled device. It is uncontrolled device. Switching on and off is not in our control in the diode, but switching on at which angle, that is in our control, but switching off is not in our control. If you see the modes of operation, there are 3 modes of operation for a silicon controlled rectifier SCR, depending upon the biasing given to it. The forward blocking mode is a one mode, that is off state, and the forward conduction mode, that is on state, and the reverse blocking mode, that is off state. There are 3 modes we are having in the SCR. We will discuss each and every mode clearly. Forward blocking mode. In the forward blocking mode here, we are giving, this is the total SCR PN. There are 4 layers and the 3 junction, J1, J2, J3, and it is a gate terminal we are connecting to the P terminal. In between the gate, in between the P and the cathode, we are connecting this gate signal. But here we are not giving any gate signal in the forward blocking mode. We are not connecting any voltage to the gate signal. Just we are applying the forward voltage, that is positive terminal of the input is connected to anode and the negative terminal of the battery is connected to cathode. Okay, that is here. If you see the J1 junction here negative positive terminal of the battery is connected to P type, that is a J1 terminal, and the negative terminal is connected to N terminal. Okay, from this we can say that junction J1 is in forward bias and junction J3 is also forward bias. But if you see the middle one, that it is connected in between the N and P terminal. So here we are giving positive terminal to the N type, here negative terminal to the P type in the junction. That's why here then we can say that J2 will be in the reverse bias condition. J1, J3 forward bias and the J2 will be in the reverse bias condition. Okay, because of the J2 will be in the reverse bias, there is no charge carriers flow from P to N layers. Okay, there is a depletion layer in here. The depletion layer width will be increases as the J2 will be in the reverse bias. So that's why the current flows through the J2 junction is very low. That is a very only leakage current flows. That's why there is no conduction in the device. That's why it is called as forward blocking low. Even the J1, J3 are in the forward bias, but the current will not flow in the SCR because the J2 will be in the reverse bias condition. See here, in this mode of operation, the positive voltage is given to the anode A. See here, positive voltage is given to the anode A and the negative voltage is given to the cathode K. And the gate is open circuited. We are not giving any supply to the gate here. That this mode is called as a forward blocking mode. In this mode, J1, J3 are forward bias. See here, J1, J3 are forward bias and J2 is reverse bias. J2 is reverse bias. Due to the reverse bias voltage, the width of the depletion region increases at the junction J2. See here, if we see the J2 junction as it is reverse bias, the width of the J2 junction will be increases. So it blocks the current flows between the J1 and J3. Because of the reverse bias of the J2 junction, there is no current flows through the J1 and J3. The majority of the current does not flow between the junction J1 and J3. However, a small amount of leakage current flows between J1 and J3. Okay, the current will not flow through the J1 and J3 because here depletion region width is more, but there is a small leakage current flows between J1 and J3. In this mode of operation, SCR is in forward bias, but still the current does not flow through it, hence it is named as a forward blocking mode. Even the J1, J3 are forward biased, but the current is not flowing. That's why it is called as forward blocking mode. It is blocking the current. That's why it is called as a forward blocking mode. This is about the one mode of the forward SCR. In SCR, in this mode, the SCR is in off state only. It will be not in the on state. Next one is forward conduction mode. Okay, now we'll see what is forward conduction mode. The silicon control rectifier can be made to conduct in two ways. In the forward conduction mode, we can made to conduct in two ways of the SCR. We can conduct the SCR in two ways. The first way is by increasing the forward bias voltage applied between the anode and cathode beyond the breakdown voltage. If we increase the forward voltage beyond the breakdown voltage, the SCR will be in the on condition. By using the next method is by applying the positive voltage at the gate terminal. Okay, so in the previous case we have not given any input, any supply to the gate signal. Gate signal is open circuited. Now we are giving the gate signal to the SCR. Then the SCR will be in the conduction mode. Now let's see the circuit diagram here. Now in this we are talking about the first case. In the first case, same here, we are not giving any gate signal here. We are talking about the first case now. In the first case, we are not giving any gate signal. We are increasing the output voltage beyond the breakdown voltage. In the first case, the forward bias voltage applied between the anode and cathode is increased beyond the breakdown voltage. So certain breakdown voltage will be there. Beyond that breakdown voltage, we will increase this forward bias voltage. Then the SCR will be in the on condition. Okay, here we will
increase the forward voltage continuously beyond the breakdown voltage, then the SCR will be in the on condition. As a result, depletion region breakdown occurs at the junction J2 and the current start flowing through the SCR. So the SCR will be in on state. The current flows in the SCR increases rapidly after the junction breakdown occurs. Here, forward bias voltage, if we increase beyond the breakdown voltage, this depletion region at the J2 junction will be removed and the current flows between P to N layer. Then as a result, the current flows and the SCR will be in the on state. So this is about the first case. In the first case, we are not applying any gate signal here, just we are increasing the forward bias voltage beyond the breakdown voltage. Then this depletion region width will be removed and the current starts flows through the SCR. This is about the case 1. This is the case 1. Now in the second case, a small positive voltage VG is applied to the gate terminal. Here we are applying the small positive voltage here. Positive terminal, it is a negative terminal. This positive terminal is connected to the P and negative terminal is connected to the this N terminal. Then the J2 junction will be in the forward bias condition. If you see here, J1 will be forward bias condition and J2 also now forward bias. In the previous case, J2 will be in the reverse bias. See here, positive terminal is connected to P, then the J1 is forward bias. Negative terminal, this negative terminal and the small VG we are applying, this negative terminal, both the negative terminals are connected to N, that is J3 junction. Then J3 is also in the forward bias condition. Coming to the J2 terminal, see here, coming to the J2 terminal, in the J2 terminal now we are applying externally, the positive terminal is connected to this gate terminal which is connected to P layer. Then this J2 will be in the forward bias condition. Now as all the junctions are forward bias, now the SCR will be in the on state. When a small positive voltage is applied to the gate terminal, here the junction J2 will become forward bias. As it is positive is connected to P, then J2 will be in the forward bias condition. So the depletion region width at the junction J2, now it will become very narrow as it is forward bias. In the second case, we no need to apply the large voltage between the anode and cathode. In the first case, we are increasing the forward bias voltage beyond the breakdown voltage, but here no need to apply here. A small voltage between the anode and cathode and a positive voltage to the gate signal is a small voltage between the anode and cathode and a positive voltage to the gate signal is enough to brought the SCR from the blocking mode to the conduction mode. In the case 1, we are increasing the forward voltage beyond the breakdown voltage, then the SCR will be in the on state. But here the very large amount of supply voltage is required. But in the second case, a very small amount of this gate signal and a very small amount of the supply voltage is required to make the SCR from the off state to the on state. Okay, this is the advantage of the second case. Generally, we use the second case only. We will give the gate signal and we will give a small amount of the forward bias voltage. Next, we will discuss about the reverse blocking mode. In the reverse blocking mode, we will apply this negative to the negative terminal is connected to the anode and the positive terminal is connected to the cathode. Then here in the reverse blocking mode, J1 will be in the reverse bias. J1 will be reverse bias and the J3 is also reverse bias. Okay, now we'll see in this mode of operation, the negative voltage is given to the anode. See here, we are negative voltage we are giving to the anode and the positive voltage we are given to the cathode. Okay, and gate is open circuited. Gate is open circuited. In this case, the junction J1 and J3 are in the reverse bias condition, whereas the J2 will be in the forward bias condition. Okay, as a junction J1, J3 are reverse bias, no current flows through the SCR circuit, but a small leakage current flows in the forward bias junction J2. this small leakage current not enough to turn on the SCR. So the SCR will be in the off state condition. As the J1, J3 are in the reverse bias condition, even the J2 is forward bias, a small leakage current flows. This current not enough to turn on the SCR. So this is the reverse blocking mode. In the reverse blocking mode, SCR will be in the off state. Okay, in the forward blocking mode, there are three modes we are having. In the forward blocking mode, SCR will be in the on state, but it will not turn on because of the junction J2 is reverse bias. But in the forward conduction mode, as all the junctions are forward bias, SCR will be in the on state. But in the reverse blocking mode, because of the reverse bias of this both the junctions, SCR will be in the off state condition. This is about the SCR forward and reverse bias conditions of three junctions and the three modes. Now we will see the VA characteristics of SCR. So in the VA characteristics of SCR, in the x-axis we are taking the anode, and in the x-axis we are taking the anode voltage, on y-axis anode current. Here also in the third quadrant, in the y-axis in the negative region minus IA, and the x-axis in the negative region minus VA. Okay, negative anode voltage and the negative anode current, it is of plus VA and plus IA. First quadrant we will draw the forward conduction characteristics, and in the third quadrant we will draw the reverse characteristics. As both the voltage and currents are in the negative, that's why we will draw in the third quadrant. As both are positive, we will draw the forward bias characteristics in the first quadrant. Here initially we are not applying any gate signal, that's why this SCR will be in the forward blocking mode. See here, this is the forward blocking mode. Up to from year to year, there is a forward blocking mode. SCR is not conducting. Very small leakage current flows here. The current is very small. If you see here, the current is very small current flows. As the anode voltage is increases, okay, here there is very small current flows here. Now, if you apply the gate signal, okay, if we apply the gate signal, if we apply the small voltage applied between the gate signal, it starts conducting. Okay, when we increase, when Ig is equal to 0, this is the characteristics we will get. When we apply the gate signal, the SCR which starts conduct from here, and it will come to the forward conduction mode. Okay, when we give at this point, if we give the gate signal, up to this point there is no conduction. Here we are giving the gate signal, and it is increasing lightly, and it will go to this position and it increases drastically. This mode is called as a forward conduction mode. Again, if you increase the gate signal, okay, if you increase the gate current from Ig1 to Ig2, initially Ig, we are giving the Ig here. At Ig, as Ig is very small, it is taking this much time to conduct here. Up to this point, there is no conduction. At this point, we are giving the gate signal, and it starts conduct. Again, if you increase the gate signal from Ig to Ig1, we are increasing the gate signal from Ig to Ig1, so it starts conduct from this position, and it will go to the forward conduction mode. If you increase further Ig1 to Ig2, it starts conduct from this position only. Before, when gate signal is at Ig, it is taking this much time to conduct. It will go to the conduction mode. If you as we are increasing the gate signal from Ig to Ig1 and Ig1 to Ig2, it starts conduct from this position only. Okay, as we increase the gate signal, it starts conduct from this position. Okay, this is about the forward conduction mode, and this is the forward blocking. Forward blocking mode is before giving to the gate signal, and the forward conduction mode is after giving the gate signal, it will go to the forward conduction mode. This is the forward blocking and forward conduction modes of the silicon control rectifier. Okay, now when here there are J1, J3, J3 junctions are there. J1, J3 are in the reverse bias, and J2 are in forward bias. That mode is called as the reverse blocking mode. In the reverse blocking mode, up to this point, there is no conduction. If you increase beyond that point, the current increases drastically and the diode will damage. So we will not apply the voltage after the breakdown voltage. Here there is no current flows in the reverse bias. Up to this point there is very small leakage current flows only. Okay, this is the reverse leakage current of the SCR. This is the forward bias and the reverse bias characteristics of silicon control rectifier. In the reverse bias, we will operate the transistor, rectifier, silicon control rectifier up to this point only. If we increase the negative voltage beyond this point, the reverse current increases drastically and the device will damage. So that's why we will operate the SCR up to this position only. This is about the VA characteristics of SCR. Now we'll see the applications of silicon control rectifier. The SCCRs are used for the home applications. Controls include, first one is lighting, and the second one is temperature control, and the third one is fan speed regulation, and in the heating application, and as well as the alarm activation. So these are the home applications we use the SCR, silicon control rectifier. If we take the industrial applications, that is the large power applications, used to control the motor speed, we use the SCR. And for the battery charging also we use SCR. And for power conversions, we use the SCR. This is about the silicon control rectifier and its characteristics and the different modes and the applications. Okay, in the next class, we will discuss about the one more special purpose devices, that is Schottky diode. Thank you.